Greetings, students. I've put together this video since I'm sick at home today, so hello from my kitchen. And we did want to talk about a couple of things today, and we're on a tight schedule, so I just wanted to give you some video stuff so that when we meet again, this isn't completely new. And it's dealing with sections 10.4 and 10.5 in the book, which talks about what happens to kinetic energy and rotation. And in the process of talking about that, we need to start talking about something called moment of inertia, which is the rotational analog to the concept of inertia, or mass. And we've already seen in the kinematics parts that we have rotational analogs, like there's angular position for position, there's angular velocity for velocity, and not surprisingly, angular acceleration for acceleration. So I took these pictures and some of the equation-y stuff straight from the book. And in this picture, there is a random amoeba-shaped object that's going to rotate with an angular velocity omega. And it's rotating about this particular axis that they're calling the z-axis. And it goes through this spot O here. And it could hypothetically be rotating about any spot here. This axis could be here. The mathematics would end up giving you the same basic result. So the question being, what is the kinetic energy of rotation of an object like this? We think of kinetic energy in terms of an object moving translationally, like a ball falling or a car moving, and it has to move in XYZ space. But what about an object that's just spinning and not even moving? Like, what about just a spinning ball? Does it have energy by virtue of that spin? And the answer is yes, and we think about it in terms of the fact that the ball is actually made up of little discrete chunks of mass. So in the context of this problem here, this amoeba-shaped blob, you could think of it as being made up of all sorts of little mass elements. Like this one right here, called Mi, is just one little chunk of mass that makes up the entire disk. You could think of it as consisting of lots of little chunks of mass all over the place. And that each little chunk of mass actually has its own speed v, which is shown in this red vector here, by virtue of its placement along the disk. Now remember that there's a relationship between linear speed and rotational speed, given by v is equal to r omega. So if the entire disk has a constant omega, it spins at a constant angular velocity, then every little piece that makes up, every little dm here, little mass element, has a little kinetic energy, given by 1/2 mv squared. The v's will keep changing as you get radially further outwards. So we think of the rotational kinetic energy, which is being shown here by Kr, as the sum of all the little kinetic energies, 1/2 mv squared, for the little mass elements, all added together. So we're using the sum notation here. And so if you add up all the little 1/2 mv squareds, you end up getting this term here. And really this term just comes from the fact that the speed of each one of these little mass elements can be written in terms of r omega. So if you replace this vi here with r omega, you get this term, 1/2 times the sum of all the little masses, their positions relative to the rotational axis squared, and then their angular velocities squared. Now the benefit is that all these little dm pieces all have different velocities. Like a piece here would have a small velocity v. This piece has a velocity shown by this arrow, but a piece out here should have a really, really big velocity v. Those are all changing, but omega is the same for all of them. So you could actually kind of pull this together and say the total rotational kinetic energy is just 1/2 times omega squared, which is the same for every piece. And then this is the term that you have to add up for every little piece. So it's the sum of all the little mass elements times their position squared. And the position is this vector here. It's a position from the axis of rotation out to where the object is located. It's kind of like a radius, I suppose, if the object is traveling in a circle around that spot. So you end up with r as the variable. And you might notice some similarities, because kinetic energy translational, which means linear kinetic energy. It's the kinetic energy you already know and love. It's 1/2 mv squared. You might notice that these look similar. They both have 1/2s. They both have something involving speed squared. So this term must be kind of like the rotational version of mass. And this is the moment of inertia. And it involves not only mass, but also where the mass is located relative to the rotational axis. And this says that you can find the moment of inertia of a series of point masses by multiplying the point mass's mass times its location squared, and then adding up all the different point masses together. And I have an example of this in the next slide, I believe. Okay, that was a very annoying sound. And I will get rid of the sound now, as you probably just saw. So here's a problem from the book, and this problem is going to involve finding the moment of inertia for a series of point masses, and then finding out the rotational kinetic energy of that arrangement of masses while it's rotating. And the problem is number 22 from chapter 10. So there's this rod. It has 3 particles, and they're attached by these massless rods. So it's not even so much a rod as it is 3 particles kind of attached to each other by a massless rod. And this whole system can rotate about this point 0. And you can kind of see the direction of the rotation would kind of be, this one would be coming out at you, these two would be going into your screen, and the whole thing just rotates around. First, let's find the moment of inertia of this arrangement. The moment of inertia is the sum of all the masses and the respective positions squared. So for this, there's 4 different terms. So I have 4 different terms to add up, and each one of these is just the mass. So for the top one, 4 kilograms, and its position is 3 meters from this spot right here, which is the rotational axis. And then plus 2 kilograms, this object, and its position is 2 meters from the rotational axis. I didn't even bother with the negative here. It's going to get squared anyway. And then the same thing for this piece. Multiply each term, add them together, and you get 92 kilogram meters squared, which doesn't really, as a unit, isn't terribly exciting. It's just the unit for moment of inertia. Again, it's kind of the rotational analog to mass. If mass is how difficult it is, if inertia is how difficult it is to accelerate an object, then this number tells you how difficult it is to rotationally accelerate this object. So if there's more mass further away from here, because of this r squared term, if you put mass farther away, it has a huge effect on your ability to angularly accelerate it, because that r term is squared. If you double the mass distance away from the axis of rotation, it should quadruple how difficult it is to angularly accelerate it. Pardon me. So now that we have I, we can calculate the rotational kinetic energy of this arrangement. We're told in the problem that it's rotating at 2 radians per second. That's a little less than a full rotation. Actually, it's quite a bit less than a full rotation per second, since a full rotation would be 2 pi radians. So the mathematics of this rotational kinetic energy is given by this formula then, which we saw in the previous slide. It's 1/2 I omega squared, where I is the moment of inertia, and omega is the angular velocity of this apparatus here. So I plugged in 92 for I, 2 radians per second, squared here, and worked it out to 184 joules. Reasonably straightforward, nothing particularly crazy about this. It's probably important to highlight the idea that rotational kinetic energy is not a new form of energy. It's literally the translational kinetic energy of all the things that are spinning around in the circle added together. And that would be the energy of this thing. If you think about this thing rotating around, its center of mass isn't moving left, right, up, down, in, or out. So you can't calculate a linear kinetic energy or a translational kinetic energy for the object. But you could calculate the translational kinetic energies of all 3 parts of it relative to this. And that's what rotational kinetic energy is. So an object that's moving can have both a linear kinetic energy and a translational kinetic energy. We'll see that in the problem in a minute. Part B of this problem just wants you to find out the speeds of all of these objects and then calculate their translational kinetic energies, show they equal the rotational value, and they do. You could figure out how fast each ball's moving by just using the V equals R omega thing we saw in class yesterday. It relates the linear speed of an object to the angular velocity of the object. So you get the speeds here, and then you can do 1/2 mv squared for all 3 objects and add them to get the same number that we got here. So a little more on the moment of inertia idea. It's rare that we're really studying a series of point particles, like 3 discrete objects connected by massless rods. Usually when we're studying something, it's a rigid object, which is a continuous stream of mass, like say a rod or a rectangular sheet or a cylinder, or a disc, or a hollow cylinder, or a sphere, the ever popular sphere, which is basically a ball. So there are formulas for these, and you can calculate them too, but these formulas are a pretty good idea to memorize. They're usually given on AP exams, but it's sometimes quicker if you just have them handy. And so the I values that are given here are with respect to the center of mass of each of these objects. If it says ICM, and then there's the exception over here. This is a rod about its end point, so that's not for the center of mass. And I'll show example calculations for a couple of these. And but you can calculate these because if you think about the limit of the moment of inertia equation, as the mass gets closer and closer to zero, in other words, you're taking this and thinking of, like, say, a cylinder like this as little chunks of mass, and you're calculating I for the infinitely large number of masses that make up this thing, and take all of those terms and add them together, you're basically shrinking m down to 0, and you're solving this, which is an integral. So it's the integral of r squared dm, and we'll show how to use that in a future slide here. But example, how do you use this chart? If you want to find the kinetic energy of a baseball, the total kinetic energy of a baseball, not just its kinetic energy because it's moving in a direction, but also because it's spinning while it's moving. That would be the addition of its translational plus the rotational terms here. So the question is, what's the total kinetic energy of a 0.4 kilogram baseball, so we know the mass, moving at 22 meters per second, so we know its linear speed, rotating at 35 radians per second, we know how fast it's spinning now, assume a radius of 0.06 meters and a uniform density. And the uniform density is important because it allows for us to model the baseball as a solid sphere. So the total kinetic energy is the sum. So here's the translational, which is just 1/2 mv squared. It's just pulling the numbers out of here and plugging it in and getting 96.8 joules. Now the rotational term is 1/2 I omega squared, and I for the baseball, if we're modeling it as a solid sphere, is 2/5 mr squared. So if I then plug in all the numbers given in the problem, we get a not so hefty number here of 0.35 joules. So when you add these two numbers together, you will get the total kinetic energy of the baseball that is moving and spinning together. So just two more slides, and I'll try to go through them sort of quickly, but they're pretty math heavy. I'm going to show the example calculation of how you get this one. Like, how do you actually use this integral to calculate the moment of inertia of a rod spinning about its center, and how do you use this integral to find the rotational inertia of a disk, a cylinder of mass rotating about its center. And it turns out it actually could be a disk too, that the length of this disk from here to here, the length of the cylinder, doesn't matter. In fact, you can see in the math here, there is no term for how long the cylinder is, just the radius and the mass. So those terms are up here. Here it is for the rod. So for the rod, imagine that you have a rod, and this is kind of the view of it along the side, and it's going to be rotating through the center, so almost like a baton twirling, as it were, and it's of uniform density all the way through. So the total mass of this rod can be thought of as m. M is the total mass. And then this value here, L, is the total length across the rod, and it's going to rotate about this axis point right here, O. So if we consider right to be positive, we can locate positions along this rod, positive to the right and negative to the left. So the mathematics of the moment of inertia, the integral of r squared dm for this shape, will give us its moment of inertia. And the trick to these is trying to write the integral not in terms of mass, but in terms of position, because that's the variable that we have here. And the way that you generally go about doing that is by thinking of the idea of the density. The density of this particular rod, since it's very thin, can be thought of as a line density, that it's mass per unit length. And if it is uniform, then the total mass divided by the total length should equal the mass of a little chunk here, dm, times its little length, which they have here in the picture as dx, but I'm using dr for. That the ratio of mass to length should be the same, whether it's the whole rod or of an infinitesimally small piece of the rod, because the density is uniform. So I can rewrite this. I can rewrite rho is equal to dm over dr by getting dm by itself and saying that's equal to rho dr. And that's really the key to doing this problem, taking this rho dr term and then plugging it in here for dm, and then you have an integral with respect to r dr. Now, density can be rewritten over here as m over L, the total mass over the total length. So I'll plug that in over here. I can pull m over L out in front of the integral, and then the limits of my integration, I'm going to integrate from here, which is minus L over 2, because it's to the left of the 0 here, and its total length is L, so this is L over 2, and then all the way out to here, which is positive L over 2, those become my limits of integration. And then I integrate this. The integral of r squared dr is just 1/3 r cubed, and then I do a bunch of the math. When you get to here, this term is on the next page as well. Starting from here and then this churning through the math, you get 1/12 ml squared, which is indeed what is on the chart for a rod through its center. And we'll talk in class about why the rod through an end ends up being 1/3 ml squared, which is significantly more than 1/2 ml squared. It has a lot to do with the idea of where the mass is again. If you have a rod of mass m and length L through the center, and that same rod rotating about the edge, in this case you would expect a larger value of I than here. You would have a smaller value of I because so much of the mass is far away from the axis of rotation, and ultimately I is equal to the integral of r squared dm. R is very important. If there's mass further away, it contributes more than just there being mass at all. So the fact that there's a lot of mass at a great distance r away from the axis of rotation makes this 1/3 ml squared, and this one 1/12 ml squared. And then even more complicated than that ends up being the cylinder term, and we'll take a look at this one as well. For the cylinder, what you're thinking of doing here is taking this cylinder and finding the moment of inertia of infinitesimally thin rings of mass with length L. So kind of like shell cylinders all the way out to R, which is the radius of this uniform density cylinder. And there's a couple of tricks to this one. Again, starting with I equals the integral of r squared dm, we're going to go back to the idea that we want to rewrite dm in terms of r. So the density is equal to mass over volume, which should also be dm over dv. And here we are using volume, because this is a three-dimensional object that we are going to have to, we can't play the line trick with a very, very thin rod. So writing this in terms of dm, we have rho dv, and dv isn't r. We'd like to have a dr term so we can take the integral of r with respect to it. So there's a couple of ways we can go about doing that. One of them is saying that dv is really just L times dA, because if you take the area of one of these and then multiply it by the length down, you will have the volume. So rewriting dv as L dA, and then dA, we have to try to figure out how to write that in terms of r. And there's a couple of ways to think about it. You could think about it as dA is really just 2 pi r dr, where the area of one of these infinitesimally narrow rings is going to be the circumference of the ring times the thickness dr. Another way to think about it is starting with the area of a circle, which is pi r squared. And if you take the derivative of the area of a circle with respect to the radius, you're essentially getting the circumference. The circumference is how much the area changes for every amount of infinitesimally increased radius. And then you get the same thing, that dA is related to r as equaling 2 pi r dr. So that's how we can replace dA with 2 pi r dr. And when we do that, and we plug it into the dm term here, we'll end up getting I is equal to the integral from 0 out to r of r squared rho L 2 pi r dr. Because again, we're taking this, we're plugging this in for dm. dV is really L 2 pi r dr. So we have rho L 2 pi r dr. And if that isn't enough, remember that we have to plug in for rho as well, which is the density of the entire cylinder. So the density of the entire cylinder, you could look at out here. It's mass per unit volume. Well, the volume of a cylinder is 2 pi r, and here I'm using capital R. And it's important to differentiate between capital R's and lowercase r's. The capital numbers are the values for the whole cylinder, so r is the total radius out to the edge of the cylinder. But little r is just a position variable going out from the axis of rotation out to the shell we're talking about. So the volume of the whole sphere and the volume and the mass of the whole sphere are in this term. So 2 pi pi times r squared times L. This is the density of this entire cylinder. And if we plug that in for rho, we end up getting this lovely mess that we have to do something with here. There's some cancellations happen. These L's go away, these pi's go away, and we can pull out a lot of things here. Capital M is constant. Capital R is constant because it's the radius of the cylinder. And then this 2 we can pull out, and then we can simplify this to look like this. That the moment of inertia for this cylinder rotating about its center should be 2m over r squared, and the integral from 0 to r of r cubed dr. And I'll show that in the next page as well. If we start from here and we do that integral out, the integral is 1/4 r to the 4th from 0 to r, work out the math, and we get the answer that's in that table once again, that I is 1/2 mr squared. The number of times that you're going to have to actually do all these calculations with integrals to find moment of inertia are probably 0. They have come up very occasionally on the AP test, and usually it's the rod type problems, not dealing with cylindrical or spherical shells. But it's something to take a look at, and it's kind of interesting calculus as well. But more often than not, just memorizing these values and then using them in problem solving is what's most important. And thanks for taking some time to look at these topics tonight, and hopefully tomorrow we can go over some of these ideas and look at all the homework assignments. All right, take care.